Hi there, I'm Ling. I'm a software engineer, hobbyist game developer, and recent graduate from the University of Chicago. In today's code interview crash course, the topic we will look at is graph traversal. We will cover two common graph traversal techniques, depth first search, DFS, and breadth first search, BFS. We will first learn about how they work and how to implement them in code. Then we will see the algorithms in action by solving a LeetCode problem, as well as looking at how I applied graph traversal when implementing an algorithm for my game, Clicky Galaxy, which is also my first game built in Unity when I was learning Unity. Let's get started. We may represent the graph by mapping each node to its list of neighbors, as shown in this Python snippet. So 0 has neighbors 1 and 4. 1 has neighbors 0, 4, 3, and 2. 2 has neighbors 1 and 3. 3 has neighbors 4, 1, and 2. And 4 has neighbors 0, 1, and 3. Now let's look at how to implement depth first search and breadth first search in code. First, depth first search. As its name suggests, depth first search prioritizes depth in its search. For a given node, say 1, after visiting one of its neighbors, say 0, instead of visiting the rest of the neighbors 4, 3, and 2, it caches those neighbors and immediately resumes its visit on 0's neighbors, which in this case is 4 since we already visited node 1. Only when it has exhausted the depth will it return to those cached neighbors down here. So we define our graph like this. Let's first implement depth first search. DFS is short for depth first search, so we want to take in a graph and a starting node. So we keep track of a list of nodes that we have visited so that we don't visit it a second time in case there is a loop in the graph, and a stack of nodes that we need to visit. So this is a list that only contains our starting node. While there is something in our stack, we know there are more nodes to visit. So we pop off from the stack. And if the node hasn't been visited, we can perform some operations on this node. So for example, here we print out the content of the node. And now that we have processed the node, we add the node to visited. And now, because we prioritizes depth in our search, we need to cache our immediate neighbors. Because graph is a dictionary, this is how we look up the list of neighbors for this given node. If the neighbor hasn't been visited, we add the neighbor to our toVisit stack. The append method will add this neighbor to the end of the stack. Then in the next iteration of the loop, we pop this node off from the end of the stack and process it. Then we continue appending its neighbors and resume the visit on one of its immediate neighbors. Relative to our starting node, we are effectively visiting its neighbor's neighbor. And that's how we go deep in our search. And by the very end, we want to return visited so we can sanity check that we have visited all the nodes in the graph. Now let's print out our result. So I'm calling DFS on the graph with 0 as my starting node. The traversal starts at 0 and then go to 0's immediate neighbor 4. And then it went deep again, going to 4's neighbor 3 and 3's neighbor 2. And then because 3 has already been visited, the only node that is left is 1, and our traversal ends on node 1. This is depth first search. Let's move on to breadth first search. Breadth first search prioritizes breadth in the search. For a given node, let's say node 2, it will visit all of its immediate neighbors, node 1 and 3, before moving on to the neighbor's neighbors, for example, 3's neighbor 4. This is how we implement breadth first search. Again, we keep track of a visited set, and this time we're using the queue instead of a stack. So we're going to from collections import deck, which is a double-ended queue, and our toVisit queue will be a deck containing our start node. A deck, a double-ended queue, will allow us to pop off nodes either from the left or from the right, and to append to either the start of the queue or to the end of the queue. While we have something in our toVisit queue, we pop off the first element of the queue. So this time we use node equals queue dot pop left, because we want the first element. And then just like what we did for depth first search, if the node is not in visited, we perform some operations. So for example, here we print out this node. And now we're done processing the node and we add it to our visited set. Now it's time to handle the neighbors. For the node's neighbors, if the neighbor hasn't been visited, we put them to the end of the queue. And as a sanity check, we return every node that we have visited. Now let's see what happens when we run this code. So we do a breadth first search on our graph defined above, starting from the node 0. So starting from node 0, we first visit 0's immediate neighbor 1, and then we visit the other immediate neighbor 4. And then we have 1's neighbors 2 and 3. We're not visiting 4 again because 4 has already been visited. Great. So this is how we implement breadth first search and depth first search. Easy as that. Now that we've seen how to use DFS and BFS to traverse the entire graph and print out the whole traversal history, we can make some small changes to the templates to find a path between any two nodes in the graph, if such path exists. On a graph where each edge has the same weight, BFS is equivalent to Dijkstra's shortest path algorithm. It finds the shortest path, which is the path with the fewest number of nodes between a source node and a destination node. This is a nice property that only a path search with BFS but not DFS has. Here is how we adapt the DFS template to return a path given a source and a destination node. So instead of start, it takes in source and dest. And we make some changes to our stack so that it caches both the source node and the current path, which is displayed in a list of nodes. So while stack, we are popping off both the node and the current path, because now that each item in our stack is a 2-element tuple. If the node hasn't been visited, we check if the node is our destination node. If so, we return the path. Otherwise, we simply add a node to the visited list. Then, for neighbor in the list of neighbors, if the neighbor hasn't been visited, we append to the stack a 2-element tuple. So our element will be the neighbor and our path so far concatenated with the neighboring node. And we append this element. Here, instead of visited, we should return none, because if the path does exist, we should be able to identify it when we visit a node and return the path here. If we go down to this part of the function and exhaust everything in the stack, meaning that we have traversed the entire graph and haven't found a valid path, return none. Great. Now let's do DFS path. From node 0, let's do to node 3. Alright, so the path it has chosen is 0, 4, and then 3. Now that's the path search with DFS. Now let's do BFS. So again, we rename this function to BFS path, passing in a source and a destination. And here, instead of a 2-element tuple, like in DFS, we only use a path. While we haven't exhausted every node in this graph, the thing we're popping off is actually the path. And our current node will be the last node on our path. If the node hasn't been visited, if the node is equivalent to our destination node, we can return path. Otherwise, we mark the node as visited. Then, for each of our neighbor, if the neighbor hasn't been visited, this time, instead of simply appending the neighboring node to the queue, we append the current path plus the neighbor, because we are considering this neighbor in our path. Down here, instead of returning visited, we return not, because if we have exhausted the graph but has not hit here and return a path, That means that there is no valid path between the source and the destination node. So this queue here will actually contain a list of paths. To make this more concrete, let's run the code. So let's say we want to find a path between 0 and 3. And breadth search suggests that we do 0, 1, and 3, which is the shortest path since we're not doing 0, 1, 2, and 3. Alright, before I demo how to solve a problem on LeetCode by applying BFS, let's familiarize ourselves more with BFS by looking at this very straightforward HackerRank problem, breadth search, shortest reach. The problem is as follows. We consider an undirected graph where each edge weighs 6 units. Each of the nodes is labeled consecutively from 1 to n. Feel free to pause the video and read the problem statement yourself. The problem is asking us to determine and report the shortest distance to each of the other nodes from a given starting node using the breadth search algorithm. And for unreachable node, we return -1. The input is the number of nodes, the number of edges, a list of edges, which we should convert to the graph representation, the dictionary representation that we are more familiar with, and the starting node. So we have n, m edges, and s. And we want to output an array that is one element smaller than the input number of nodes because we want to exclude the start node from our return distances. Now let's try to solve this problem. Let's copy over the BFS template. Now we want to, from collections, import deck. Before we do anything, let's convert edges into our graph dictionary representation. So our graph is a dictionary. The nodes are numbered from 1 to n. So for each one, we initialize an empty list of neighbors. And then for each node in the edges, because it's an undirected graph, we add the neighbors for both of the nodes. Alright, and now we have our graph representation that we can use. Next, let's keep track of a distance dictionary that maps each node to the distance between it and our source node. And here in our deck, we put in a tuple. So we want the source node and the distance. It might be better if I name this as cost because each edge weighs 6 units. So cost. Now, this time we're going to put the source node into the visited set, and instead we'll process the node when we see that it's a neighbor of the current node that we just popped off. So we pop off a node and the cost from the starting node from the queue. And then we look up the neighbor in the graph. If the neighbor hasn't been visited, we mark the neighbor as visited because we're processing it right now. And our costs of reaching this neighbor will just be the cost we just popped off plus 6 because each edge weighs 6 units. And here I'm just going to make a variable named new cost. And then this will be equal to new cost. And then instead of simply appending the neighbor to the queue, remember that each element in our queue is a node cost tuple. So neighbor, new cost. Instead of returning visited, we want to return an array of distances from the start node in node number order. So we filter out the start node. So ret is an empty array for node in range I n plus I. If node is the starting node, we continue. And if it's not the starting node, we get the cost. We will give it a default cost of -1 in case the node is not reachable and has never made its way into our costs dictionary. And we append the cost to our return. And we return our return. All right, let's run the code. We passed the 2 sample test cases. Let's submit the code. Great, and just like that, we solved this breadth search shortest reach problem on HackerRank. Next, we'll see a LeetCode problem. Now, let's apply what we learned about Graph Traversal to solve a problem on LeetCode. We're going to solve 758 is graph bipartite. The problem is that there is an undirected graph with n nodes where each node is numbered between n and n-1. You're given a 2D array graph where graph U is an array of nodes that node U is adjacent to, which is the graph dictionary representation that we're familiar with. More formally, for each V in graph U, there is an undirected edge between node U and V. The graph has the following properties. There are no self-edges, there are no parallel edges, the graph is undirected, the graph may not be connected. A graph is bipartite if the nodes can be partitioned into 2 independent sets, A and B, such that every edge in the graph connects a node in set A and a node in set B. Feel free to pause the video and look at those examples yourself. The definition of whether a graph is bipartite is not our main focus today. According to this Geeks for Geeks article here, to check whether a given graph is bipartite or not, all we need to do is to apply this algorithm. All we need to do is to modify our BFS algorithm. So we will assign the red color to the source vertex, color all adjacent neighbors with blue, and color all neighbors neighbor with red. We try to assign color to all vertices such that we only use 2 colors, red and blue. While assigning colors, if we find a neighbor who is colored with the same color as the current vertex, then the graph cannot be colored with 2 vertices, and the graph is not bipartite. Again, feel free to refer back to this article if you'd like to learn more about what it means for a graph to be bipartite. For now, I'm just going to apply my BFS algorithm and solve this problem. So again, we copy over the BFS template. Then up here, I will define two integers for the red color and the blue color. And we will, from collections, import deck because we're using it as part of our BFS template. The visited is just a set. Here we have a deck. All right, let's start writing the code and adapting our template. So first and foremost, if there is no graph, that means that the graph is not bipartite. We return false. Then we do the standard BFS. Our queue should initially be empty, and we can loop through the vertex like this. Because the graph is a dictionary, the length of the graph will be the number of the vertices. So for every vertex, if the vertex is invisited, we continue. Otherwise, we append the vertex to our queue because we are going to visit it. I'm using vertex here because down here, I will be referring to the nodes as nodes. And it's just another name that we can refer to the nodes in the graph. And we do node colors equals the starting vertex is red. Now this is the familiar part from our BFS template. While the queue is not empty because we just put some vertex into the queue, we pop off the node from the start of the queue, from the left of the queue. And here we do not need to process it, we just add it to visited. Here we are looking up node colors to identify the color of the current node. Well, how do we populate the node colors dictionary? We will do that when we are processing the neighbors. So for neighbor in graph node, which will be the immediate neighbors of the current node, we can check if it's bipartite by checking whether the colors matches as outlined in the Geeks for Geeks algorithm. If the neighbor has already been assigned a color, and the color is equal to the color of the current node, then it's not bipartite. It's not bipartite. And the color is same as the color of current node. If this check passes, we can proceed. If the neighbor is not visited, we append the neighbor to the queue that we will visit. And we assign color to the neighbor. If my color is blue, we want to assign the neighbor as red. So node colors neighbor var equals red. Else, if my color is red, we want to assign the neighbor to the opposite color, blue, like this. If we have iterated over the entire graph without hitting this false return, this means that the graph is bipartite, and we return true. Let's run the code. And let's submit the code. And that's how we solve this is bipartite problem with simple BFS. Alright, before I end this video, I want to show you another forum demo about Graph Traversal, which is Clicky Galaxy, a casual match 3 game I built when I was learning Unity. You can play the game either on Unity Play or itch.io. I have the links in my GitHub repository. The idea of the game is very simple. You move a planet to an empty cell and score when there are 3 or more identical planets aligned horizontally or vertically. A planet can only move horizontally or vertically but not diagonally, and its movement path cannot be obstructed by other planets. Alright, so that was my game. I actually applied Graph Traversal to check for a valid path between the planet the player clicked on and the destination cell to determine if the planet can move to that cell. Each cell in the grid is a node and has 4 immediate neighbors, up, down, left, and right. As I want to find a short path between the source and the destination, BFS pathfinding is ideal for my use case. Here is how my code looks like in C#. I have those breadth search function, which uses a helper function named getNeighbors to get the 4 immediate neighbors up, down, left, and right, ignoring out-of-bound ones. So this is just incrementing the x-axis by 1, incrementing the y-axis by 1, decrementing the y-axis by 1, decrementing the x-axis by 1 if the cell is still within the boundaries. And in my breadth search, we have the visited hash set, the path queue, a starting path, which is a list, and I added the source cell to it, and then enqueued the starting path to my path queue. While there's something in my queue, I dequeue it from the path and retrieve the node as the last element on the path. And then if my node has already been visited, I continue. If the node is equivalent to the destination I'm looking for, I return the path. Then I parses the neighbors as we did in Python. For each of the neighbor, I decide whether the destination can be visited. If so, I add it to the path and then enqueue this new path. If at the very end I could not find a valid path, I return none. And here in my function tryMoveCell, I call this breadth search function, hoping to find a path. If there is no path, tryMoveCell will return false, and the player wouldn't be able to move the planet to a cell. My game came together really well with this algorithm, so graph search can both be fun and practical. And that concludes our crash course. In this crash course, we learned about the 2 graph traversal algorithms DFS and BFS. We saw their implementation and then in action in a LeetCode problem, a HackerRank problem, as well as in my game. If you enjoyed graphs, a thought exercise I have for you is to think about how they relate to trees. Spoiler alert, pre-order traversal in trees is essentially DFS in graphs, and level order traversal in trees is essentially BFS in graphs. Try figuring this out on your own, or refer back to my crash course on tree traversal for a refresher. I hope you enjoyed this video. Please subscribe for more content like this, and I'll see you in the next one.